Test functions and distributions. In previous situations, we study linear bounded operators or linear continuous operators in norm space. So we study linear continuous operators and functionals in norm spaces. But for many applications, the norm space is not a convenient instrument. In many applications arise linear spaces without norm. More precisely, we consider so-called prenormed spaces. So definition of polynorm. X is prenormed space or polynormed space or local convex. Local convex space. If on X we have family of semi-normed, P alpha, where alpha is from some set of indexes, maybe not countable, maybe larger than continuum and so on. So our construction X is a linear space with family of semi-norms. Convergence in this space we say xn goes to x if for any alpha p alpha xn minus x go to the 0. Moreover, every time we consider the prenorm space with additional condition on this family of semi-norms. So we say that family of semi-norms distinguish points if for any pair x, y such that x is not y, there exists semi-norm p alpha such that this semi-norm gives us non-zero on different points. And this situation, why it is important condition? Because in this situation we have a uniqueness of the limit. If semi-norms can't distinct different points, so we can obtain different in this definition different limit points for unique sequence. But if we say if we take additional condition that this family distinguish points, then it's guarantees for us the uniqueness of the limit. A few minutes later, I described the topology approach for these spaces. But I repeat that if we consider prenormed space, polynormal space, we always assume that this family distinguishes points. It guarantees us the uniqueness of the limit. Topology approach. Any prenormed space is topology space. The base of topology in prenormed space is such sets, such balls or standard balls. So it is a ball with the center at x0, radius epsilon, and describes with some set of seminorms. So it's all x in x such that for any I n so it is so-called standard balls in prenormed space, and it is easy to see that the convergence in this sense coincides with convergence in topology sense. As topology, so it is base of topology. So any open set, n plus empty set, of course, by axiomatic of topology spaces. And open set is an arbitrary union of sets of such types, of standard balls. And easy to see that it is just this is epsilon x alpha. The center at x, not epsilon, alpha for it goes to the zero, so it is for any epsilon positive, you can say. In this definition, we take only such, for example, 1 over n. We take such balls and we immediately obtain this convergence. So if you take convergence in topology, we immediately obtain this. And if we take this, then of course, for any finite number, we have a convergence in topology. Let's consider this example. Some typical examples. Let's consider space S of all infinite sequences. All sequences. With standard linear operations, the coordinate sum and multiplication any coordinate on the number. So it is obviously linear space, and I consider it with a countable many seminorms. For examples, it is the absolute value of the nth coordinate. So n equals 1, 2, and so on. Second example, let's consider so-called continuous function C sub e, every, from the word every. So this continuous function on 0, 1 functions with point-wise convergence. If you want to obtain point-wise convergence, so you must obtain convergence at any point. So let's consider Pxf. So the index x is a point. X belongs to the 0, 1 point. It is absolute value of function f at point x. So here we have a continuum of polynomials. And it is to check that the convergence in this set of seminorms coincide with the pointwise convergence. It's obvious because this seminorm just gives us a pointwise convergence. And come back to the name of the lectures, the test functions and distributions. What is distributions? Distributions will be the will be linear continuous functionals on special semi-norm spaces, on special pre-norm spaces or polynorm spaces of special type. But first we need to define the continuous operator between two pre-norm space. In two pre-norm space. And in norm space, we know that any continuous linear operator is a bounded operator. In pre-norm space, we have no instrument to define the bounded operator, but we have an instrument to define continuous operator. So definition is following. Let X with set P alpha and Y with the set Q beta are pre-norm space. So it is this linear spaces with converging, which is defined with the set of pre-norm, and these sets of pre-norm distinguish points. And then we have a linear operator. So it is linear operator, operators from X to Y. We consider only linear operators, and we say A is continuous. Operator from X to Y if for any beta, so here alpha from lambda and here beta from gamma, for example. From beta from the gamma, the set of indexes for space-wise, they exist positive constant C, alpha 1, alpha n from lambda, such that for any x from x capital, Q beta AX can be estimated by linear combinations of pre-norms from the space X. For example, if on the space X we have one norm, if we have P alpha just a norm in X and Q beta one norm is a norm in space Y, this is a definition of bounded operator. If we have only one norm in X and one norm in Y, because we just it is AX less or small this. But if we have a lot of a family of prenorms, a family of seminorms, so we must appreciate any seminorm from second family by some linear combinations, for some linear combinations of seminorms from the first space. And as a particular case, what is continuous functional? F continuous functional on X. So we say F is for dual space, and in this situation I use not a star but I use a prime. to distinguish situation from norm space, dual to norm space, and dual to prenorm space. If exist C capital and alpha 1, alpha n from lambda, such that for any x from x, the absolute value of f acting on x can be estimated by linear combination of prenorm. But here we have, because it is a continuous functional, so f acts from x to c, to the numbers. In C we have one norm. In C we have one norm. It's just the absolute value of numbers. So we obtain the definition of continuous functional on prenorm space. But important case that we must obtain estimated by linear combinations of some prenorm. This set depends only on functional f. And here this set depends only of operator A and index beta. Index beta. So, and as I said, distributions is a continuous linear functionals, but I miss this linear. We work only with linear operators, or linear functionals. So distributions is a linear continuous functional in special spaces of prenorm spaces and so-called test functions. So I begin with definition of the spaces of test functions. They are all prenorm space. So spaces of test functions. One remark, I will study only one-dimensional situation, but it is possible to consider the functions of many variables, but of course a lot of proofs is more difficult in technical sense, but all ideas are the same for one-dimensional situation. So first space D. This is function phi, which is absolutely have infinitely many continuous derivatives. Infinitely many continuous derivatives, and is a compact. The support of phi is a compact. What is support? Support of function. We take all at values x on R, that phi of x is not 0, and make a closure of this set. So by definition, the support of function is a closed set. But we take functions which have infinitely many continuous derivatives, and support is a compact. So of course you can consider, for example, function from this space, and here we can take x from Rn, and nothing changes in this definition. But in one-dimensional situation, you can see that we know that for this situation there exists interval AB such that support of phi lies in AB. In spite of this fact, functions have infinitely many derivatives. There are no analytic functions except 0. Let's show that this space is not empty. Consists not only from the 0 function. Of course, a trivial 0 function belongs to this space, but it is not interest functions. Let's construct some function. I introduce function psi x, which equals Of course, it is have infinitely many derivatives right to the zero and left to the zero. And it is interesting what is the property of the derivative at point zero. If you see the graph of this function, it is have exponentially small angle when the graph go to the zero. Exponentially small. But if you take derivatives by induction, it is easy to see. By induction, you can check that the derivatives have such property. It is polynomial. Of degree 2n, and again multiplicated on this function psi. And you see that this is exponentially small at zero, and it is growth as polynomial. So by L'Hopital rule, you can check that the limit at zero equals to zero. For any n maybe also equal to zero. So it is function of class C infinity on all x, Function psi. And with this function, with the help of this function, we can construct function phi, AB x, which we denote as psi b minus x multiplied psi x minus a. Of course, I consider that a less than b. And what we construct? Here a, here b. Then psi x minus y looks like this function. And to the 1, and function b minus x goes from the right to the left and limit to 1 to the left. And our function have such form, a so-called head form. So we can use some terminology as head type function. Of course, it is have compact support because it is lies on interval AB, and it is, as we show here, it is this class of C infinity at points A and B, and other points obviously in other points is have continuous derivatives of any order. So let's make this space as prenormed space. We need to work with prenormed space. So definition. Semi-norm P is available on D if for any positive A there exists C positive which belongs only on A. There exists n of A which is natural or zero, such for any function phi from d of minus a to a. It means that support of phi belongs to the interval minus AA. The inequality is valid. P of phi So semi-norm is available if for function with fixed support, it can be measured with the standard norm in class of function with n continuous derivatives. So this is what it means. This is equals this equals sum for k equals to from 0 to n maximum on minus AA phi k of x. This is standard norm in space of functions with n continuous derivatives. So semi-norm is available if it it can be measured with some constant c with standard norm. So such norm with a standard norm. Standard norm. So available, which is measured, but for function with the fixed support. With the fixed support, it's measured with standard norm. And space D is pre-normed space. With all available semi-norms. So we take this space. We take this space as a semi-norm space or pre-normed space. We take space D, linear space. It's of course linear space. We can define linear operations as a pointwise operations, and we consider this linear space with all available semi-norms in this definition. So we obtain some special pre-normed space. We obtain some pre-normed space. So let's consider some examples of available semi-norms. Some examples of available semi-norms. First, standard norm is available, of course, just by definition. By definition. Second standard norm, available norm. Let's consider P of phi equals sum I said that it is an available norm. Why? Let phi belongs to D at minus A to A. So support belongs to the interval minus AA. Then, we must have a semi-norm. So let's write absolute values. So pi of phi, how we can measure it? If we know that function phi is from this subspace. With fixed support. So of course, if k larger than a, then this series contains only 0 elements. So it can be measured by, for example, because again, if k is larger than a, then it is 0. So we consider take function only with support with this interval, and I take the smoothness on larger on one that integer part of a, because a can be not be integer, but here k is integer. So you see that function c of a, constant c of a is 1, and n of a constant is integer part of a plus 1. So it is available seminorm. And the third example. Take continuous function on real axis and define such seminorm as supremum alpha of x, phi of x, supremum on real axis. But you remember that function phi is finite supported function, so we can take not supremum but maximum only on support. But let's check that it is available seminorm. Easy to see that for phi belong to this subspace, we obtain that it is less than maximum of alpha of x on interval minus AA multiplicated on the normal function phi on function c minus AA. So this is constant c of A. And this is just n of A equals to 0. So we obtain all parts of definitions of available seminorm. That is available seminorm. And the question, interesting question, what you can say about the convergence in D? If you consider the convergence with all available seminorms. We say that phi n tends to the 0 in D if there exists interval AB that for any n all supports of these functions lies in interval AB. First. And second, for any non-negative integers, non-negative integers, phi n g uniformly on this interval AB tends to the 0. So we have uniformly by variables x, but any derivatives go with its own velocity. And we say that phi n tends to phi in D if phi n minus phi goes to the 0 in D. And theorem. Convergence in D with all available seminorms is equivalent to 1, 2 with all this. So if we consider space D of finite supported functions with all available seminorms, it is equivalent to this convergence. It is equivalent to this convergence. First proof. Let's consider this. And let P is available. Then for any function phi from d minus AA, and let's consider this. Take let C equal maximum A B. Take constant C, maximum of absolute values of A, B, which we have in item 1. So for any function, by definition of available semi-norm, we have pi of phi less than C phi Cn minus Cc. And look at second item says us that we have uniformly convergence of all derivatives. So for function n, and we see that function n, the support of function phi n belongs to AB. And I take C as the maximum. So by definition, we see that we have minus Cc, and this goes to the 0 for the item 2. For item 1, we take a function from this class, use the definition of a variable semi-norm, obtain this inequality, and by item 2 we see that this goes to the 0. So we obtain the convergence for all available semi-norm. For all available semi-norm, we have a convergence. We have a convergence to 0. Moreover, the widest class. So the smallest interval, of course, we obtain the convergence to the 0 too. Then the inverse. The inverse by contradiction. By contradiction. First, I suppose that there is no uniform interval. Let item 1 is not wet. So without loss of generality, our support is not compact. So we have a set. We have a sequence of points which goes to plus infinity or minus infinity. Without loss of generality, assume that there exists sequence xk belongs to the plus infinity, such the function phi nk is not 0. Oh, xk. Is not 0. Then let's take function alpha of x equals, and not n, some nk. Yes, some element of some subsequence of functions, which at these points are not 0. And nk goes to the infinity, of course. So define continuous function equals 1 over phi nk xk x equals xk, and linearly in other points. And we know that p of phi equals supremum of alpha x phi of x on all R is available. Example 3, we check it, is available, but p of phi nk, let's check here f nk xk divided on phi n xkk, not less than 1. So we have a contradiction. we have a contradiction by converging to the zero. Converging for the zero. So, but assumption, let Fn goes to the zero for any available seminorm. Let's Fn goes to the zero for any available seminorm. And then I suppose that there is no uniform interval. Then I construct a new, I construct available seminorm for which we have no convergence to the zero. It is contradiction. So it is contradiction. So first item must be valid. So first item is valid. So we conclude that there exists AB such that support of all phi n lies in then AB. And then standard norm is available. It's example 1 in our examples of available seminorms. So we immediately obtain item 1. Because item 1 just as uniform, is 2. Sorry, item 2 is valid. So it's just a uniform convergence of all. You can take any standard norm with any order of n, with any order of n. So you immediately obtain that all derivatives converge to the zero. So we obtain, we have a space of finite supported function, so named space D. It is seminorm space, which gives us such interesting convergence and exercise. For anybody who is interested, this convergence is not can be said by matrix. It's not given by matrix. So the space D is not metrized space. We have a convergence. We have a convergence in topological sense. We know the base of topology in seminorm space and prenorm space, but this convergence cannot be given by metric. And definition, important definition. Generalized function or distributions is the space of continuous linear functionals on D. Okay. Examples. Dirac delta function. Dirac delta function. But it is not a function. It is a distribution. It is element of D prime. So the notation of this functional is delta of x, but it is not a value of delta at point x. It's just a notation of by Dirac of this functional. For any function phi from D, the action of function phi is the value of function phi at 0. And one remark. Before we write this, before we write the action of functional from dual space on function phi of x as following. By Dirac notation, this is a synonym for previous notations, due to Maurice Dirac, who invite this his notation. For some situations, maybe more convenient. Physics, no. So this is just another notation of action of functional f on function phi. So let's check that it is continuous functional. Let's check for this continuous functional. Y delta of x belongs to the d prime. Belongs to the d prime. Take phi from with fixed support, and it is equals and you see that it is measured by standard norm. And any available norm is measured by standard norm. So we see that, and standard norm is a class of available norms. So we see that the result of our functional on function can be measured by some available semi-norm for function with fixed support. So delta is a continuous function because we obtain measurand. Another example. But definition. Function f belongs to L1 log if for any interval AB function f belongs to L1 AB. So it is integrated on any finite interval, but it may be not integrated on all x. For example, any continuous function is a function of L1 log. Define distribution I use two letters, F capital and F small, but later we can write we will write only one letter. I explain what we have. By definition, we write the integral on all x's fx phi x dx. But of course, we define distribution for function with finite support, so it's easy to understand that for any concrete function phi, we have integral only of the finite interval. So for any function phi with fixed support, we have such estimation. Take away the maximum on interval minus AA of function phi. Of function phi. So this is constant C of A. It depends on the function f. And this is the norm of function phi in the space of continuous function. So we immediately obtain that any function of from the class L1 log define some distribution. And further, in the following discussion, I don't like I don't write two letters, I use one letter. So if we know for f class L1 log, I use one unique notation for functional and for functions. So f phi defined as integral f of x phi of x dx r. Here function f a function as L1 log, and here function f is from f d prime, and here is L1 log. They have different roles, but the element one. So I don't write two different letters for two objects. So we say that distribution is defined by the function from class L1 log, and the definition distribution is a regular. And definition if for f from the class of distribution exists function f from class L1 log such that for any phi from D the functional is defined by the integral with this local integrated function, then is regular distribution. Is a regular distribution. Other situation, another case. F is singular. What does it mean, singular distribution? There are no functional class of L1 log. So it cannot be given as an integral. Theorem, delta function is singular distribution. Maybe in physics books you can meet the notation the integral of delta, but it means nothing of no constructions of any integral. So prove by contradiction. Let exist function f from L1 log such that delta of x phi, which is equals to phi of 0, can be given as integral, can be defined as integral with this function f of x. Let's consider such construction. Let's define such functions. Phi a b epsilon, so-called smooth indicator. I just give a picture and then I prove that such function exists. It is constant, equals to 1 on the interval AB and infinitely smooth on this small neighborhood from B to B plus epsilon and from A minus epsilon to A. Of course, pointwise it's converged to the characteristic function of AB or indicator of AB. Why such function belongs to D? Why we have infinite dimension? What can looks like derivatives of this function? Here function increase, so its derivative is positive. Here function is constant, so derivative is 0. Here function decrease, so derivative is negative, and here function constant, so function derivative is 0. But this is function a minus epsilon a, b plus epsilon. We construct these head type functions This is a difference of two head type functions. So it is phi I minus epsilon A with the same square, because we want to have a zero right to the point B plus epsilon, minus phi B B plus epsilon. So we can define phi of x A B epsilon as minus of t minus phi B B plus epsilon t dt, and multiplicate it on some constant c if you want here one. If you want here one. So we have some square, but you can multiplicate it on some constant c that with normalization the square will be 1. So we obtain here 1. And let's consider function this is the main thing. So we consider A and epsilon sufficient small. A is positive, and so epsilon is sufficient small that the difference is positive. Then difference is positive. Then of course equals to 0. And this is continuous functions. And this integral, by our assumption, and this is bounded family in L1, because f of x phi A B epsilon less than absolute value of x, because function phi is less than 1 and positive. So it measurand, for example, on L1 A minus epsilon B plus epsilon. Epsilon 1 and epsilon 1 put here fixed epsilon. And then we go epsilon to the, so by Lebesgue theorem, this integral tends to this. So we obtain that function f of x, integral of function f of x on any interval ab which lies right to the 0 is 0. So you obtain that ax f of t dt equals to 0 for any x less than a less than greater than a greater than 0. Then take derivative dx. So you obtain f of x equals to 0 for any x positive. For any x positive. In the same way, what we can consider? We consider b plus epsilon less than b less than a. You consider this set of functions, this family of functions, on support with support left to the 0, and we obtain that f of x equals to 0 for any x negative. We can say nothing about point x equal to 0, but we immediately obtain that f of x equals to 0 almost everywhere. Almost everywhere. Then you immediately obtain that for any phi from D, integral f of x phi of x equals to 0, because this is 0 almost everywhere. But delta of x phi minus 1, 1 equals to 1. 1. On this function. 1, 2, minus 1, minus 2, 0, here 1. On this function we have 1. And here we obtain that it is 0 for any function. We have a contradiction. Contradictions. So let's go following and consider another space of test function, so-called Schwartz function, Schwartz space. Schwartz space. It is another space of test functions. This is defined as letter S. Its function phi infinitely smooth, so it have infinitely many continuous derivatives. And for any pq from natural numbers of 0, such semi-norms I use notation as a norm, but it is maybe semi-norm. So it is quickly decreasing functions. Quickly decreasing functions. How quickly? Any derivatives decreases faster than inverse power of polynomial, of x powered p. So any derivatives decreases faster than such functions, that any power. Of course, space D lies in S. Space D lies in S because this is a finite supported function. They goes to they are 0 outside the interval, and this is only decreased faster than these functions. Example of function f of phi of x belongs to S, of course, because it is decreases as exponential, an exponential decreasing, but it is not in D. And you see that we have this is a semi-norm, this is objects, just semi-norms in S. So we defined S just as semi-norm space. We have a set of semi-norms. So it is semi-norm space. So we can consider the dual space, the space of linear continuous functionals on S, and we define this as S prime, space of tempered distributions. It is space of linear continuous functionals on D, on S. On S. And moreover, this embedding is embedding D in S is dense n continuous. Just try to prove it. So our theorem. So of course, any function from D lies in S, it is obvious. But we need to fulfill the precedence, and first, if phi from D, of course, it is a quickly decreasing function, so phi belongs to S. Second, continuity. So let phi belongs from. What is continuous of embedding? You must show that operator of D to S, where G phi equals to phi, is continuous operator. So we take phi D of A, and you must but we take function with the fixed support, because we need to make estimations for available seminorms. And when you work with the available seminorms, by definition of available seminorm, you must take functions with fixed support. So it is less than and then we obtain CQ minus AA. This is constant CA, so we obtain the estimation for standard norm. This is standard norm which is available. Standard norm is available. And now the density. Let f is arbitrary function, phi is arbitrary from S. We construct function minus n, 1, 1, 1 of x, which looks like 1, 2, minus 1, minus 2. Here we have 1, and here we have a infinitely smooth decreasing to the 0. This is function 1. Let's consider function phi n. Phi minus n, which is looks like phi minus 1, 1, 1, x of n. X over n. What you can say about this function? It looks like it is identical one function on the largest and the largest interval. On the largest and largest interval. And let's consider function phi n, which is function phi, our function s from S, multiplied on, of course, it is from D. It has finite support. It has finite support. And what it means density? It means that we can approximate any function from S with by functions from D in seminorms in S. So you must check what happens here. You must check that for any parameters P and Q, this difference go to the 0. Go to the 0. what is phi minus phi you can write it in the following: sub on axis x pi phi of x 1 minus phi minus n brackets, and this is q of x. Let's write apart this factor. So let's investigate this object. First, it looks like first interval phi of q plus g from 1 to q phi q minus g, and here the derivative of constant 1 is 0. I take 1 first term I take when all derivatives go on phi and 0 derivatives goes here, and some derivatives go on phi, so it's minus, this is 0. I take this minus, and here phi minus n g, and g from 1. So what you can take about this first term? What you can say about this multiplicator, this in brackets? Our function phi minus n is 1 on larger and larger interval. So it is 1 on this interval. So this difference is 0 on this interval. So for 2n we go as to 1, and here minus 2n again equals to 1. Yes. Because outside interval minus 2n to n, this function is 0. But function phi is strictly increasing function. So you see that we must approximate it. For this term we obtain sub for x for this term can be estimated by this, and this go to 0 as n go to the 0. Moreover, for any power x powered p, because our function phi is strictly increasing and goes to the 0 at infinity. For these terms, what we can say about, sorry, I forget binomial coefficient, so we must write binomial coefficients, but does matter, it's some constant. This function is strictly increasing, but it is not 0, it is 1. But what you can say about this derivative? I'm sorry, I take away from the board, but it is phi minus 1, 1, 1 x over 1, and gth derivative by rule of derivative of the complex function. You have factor n power g, and g larger than 1 in all these terms. So it goes to the 0 as n goes to the infinity. So all elements from this sum goes to infinity. And x pi does depend on n. So for any powered pi, we have the factor which go to the 0. Go to the 0. So it go to the 0. So we can approximate any function from S by functions from D in semi-norms in space S. What is the importance of this theorem? because this embedding is dense and continuous, corollary is following. The set of temp distribution is a subset of all distributions. Is a subset of all distributions. So it is named all distributions or generalized function. And this is tempered distributions or tempered generalized functions or generalized functions of low growth. They can grow not larger than polynomial. And the last pair of test functions and distribution, the last pair, space E is just it is more convenient set of seminorms, but you can consider more wider class of seminorms on this space, but it is more difficult. It is more convenient of seminorms, but they gives us the same topology. So more general class set of seminorms on E. Let's compact such that, and then you can define the class, the norms on n times continuous differential functions on the compact Km. But here we have two objects, the parameter of smoothness of functions and compact. But you can make a unification of these parameters, and it is more difficult. So it is more easy. You take chi n equals to minus n with the same number, and it's easy to see that these sets of seminorms are equivalent. And it is obvious that E is subset of S. So sorry. Finite functions is subset of quickly decreasing functions, and quickly decreasing functions is subset of infinitely smooth functions. So we have no restriction on the growth of function. All infinite smooth functions, any smooth infinite functions. And as we show that D is dense and continuous in S, then this embedding is continuous and dense too. So we immediately obtain, so definition E prime is space of continuous linear functionals on E. This space is named distributions with compact support. Compact support, and we have inverse embeddings. It is all distributions, it is tempered distributions, it is distributions with compact support. But I must explain what is the compact of distribution, because distribution is not a function, it is a functional. So, and I give a this definition and then finish by some remark. Definition: let F is distribution. We say that F equal to 0 at point X if exist U of X neighborhood of X such for any function phi of D with support lies in U of X, F of phi equals to 0. For example, delta function of X equals at 1 for any X larger than positive. Equals to 0 by this definition. And support of F so support, it is a complement to all points in which our distribution equals to 0. So from the point of view of quantum mechanics, observer can't see nothing at can't see nothing at point X. And so if you, interesting theorem, if you take distribution from this space, the theorem, it is a distribution from E prime if and only if it has a compact support. So this space has a correct name. It is named distributions with compact support. It is indeed consists only from this distribution from D prime, which have a compact support from this point of view. That's all.